Okay, and we are good. All right, everyone. Hello, welcome everyone that's listening remotely to the Compute Over Data Working Group. We are fortunate to be joined with Svetly from Aligned, which is going to tell us about some really interesting work that they do building custom hardware for various compute networks. We'd like to not only cover decentralized compute networks themselves, but also the tool manufacturers that go into those, the technology builders. And so Aligned, we are first physical hardware manufacturer. If anyone's building decentralized networks, these are the guys to get in touch with to make sure you think about optimization. And then secondly, we're going to hand it over to Alexander, who's going to tell us more about the work they're doing with Petals.ml, which is a decentralized ML training network. And we're going to find out all about all of the things that are going on there. And whether or not OpenAI is actually open or not. Just kidding. Okay. So anyways, Svetly, thank you so much for getting the content ready for us. I'll hand it over to you if you're ready.
Thanks, Wes. Appreciate that. So yeah, I'm coming from Aligned. What we do is Sealing as a Service, and we're here to talk about, in general, decentralized compute. And so sealing being a specific use case that really is on the back end in the trenches of Filecoin. And so it's a great thing to discuss here and let you guys know what we're up to, and then what we can do as far as compute as a service in general. So just taking it off, we'll talk about about Aligned. So so what we are is a high performance compute company offering solutions as a service. So what we've done is our team comes from a background of video compression and rendering, where they specialize in building their own hardware for big data processing jobs. Now we've taken that skill set and applied it to decentralized networks, to blockchains, where you have big compute needs such as ZK proving, and then of course Filecoin sealing. So as I mentioned, we specialize in building our own hardware. We utilize FPGAs, and so that's a field programmable gate arrays. So essentially what we do is we take silicon from Intel and AMD, we design our own boards, we, with super fast connectors on those boards, we'll write our own software on top of those boards to take advantage of and optimize for certain compute jobs. So what we've done is basically built one of these models for Filecoin sealing. We did this back in May of last year as kind of a proof of work, proof of concept, and we presented it at Phil Austin. And what we found was it was a lot cheaper, our system, an order of magnitude cheaper than what we're seeing out in the market. So we knew we were up to something good there. So we started developing a remote sealing solution as a service. And we commercialized it back in November, and now we're commercially sealing for Filecoin storage providers. And the way our system works, on the remote sealing system works essentially is we built a remote bridge. We had to build a custom bridge that can separate out the sealing pipeline from the actual storage provider miner setup. And it's super easy deployment. Essentially, it acts just like a local worker on the storage provider side. And so you install our bridge, you set some custom environment variables, whitelist an IP, and then you can start sending jobs to our compute pipeline. And so, for very big needs, we have our data center in Ohio, Canton, Ohio. Power is great over there. Super fast internet connection, but there is bandwidth constraints on super big needs. So what we can do is essentially we can co-locate our sealing clusters in your data center, and then we can basically have a direct line connect. That opens the door for a lot of shared revenue opportunities, plus it obviously solves the bandwidth constraints. And then just kind of in general, high level for Filecoin, the Filecoin network. So what we're doing is we're trying to accelerate the Filecoin network growth. And so by decoupling sealing compute from storage, what we're doing is really helping lower the costs by allowing different storage providers or different service providers to specialize in what they're good at. So for example, if you're a storage provider, don't worry about building out the ceiling pipeline stuff, just focus on the storage. But looking at high level, about $2.5 billion of network hardware has been invested so far, with a large portion of that going towards ceiling compute. And the Filecoin network still has a lot of growth left, and so a lot of additional investment will have to be made in ceiling compute. And so this is where separating it out will really help out with this next leg of growth. And specifically for any service provider or user of compute, and in this case, storage providers who are using our ceiling as a service, the benefit to them is moving the business model away from an upfront investment in CapEx to a pay-as-you-go operating expense. And so you only pay for what you need, and it really eliminates the problems we're seeing out there with storage providers who have over-invested in ceiling compute, and now it's sitting idle. So essentially, just pay as you go and pay for what you need. Moving that CapEx to OpEx and basically optimizing that will allow storage providers to focus on storage and invest more in storage and help in that side of the business. And then also, it's complicated to build ceiling and compute systems. And so if you are a storage provider or in general, you should focus on what you're good at. So again, with the specialization concerns, storage providers can now focus on doing storage and building out, APIs for the client-facing stuff, whereas they don't need to focus on building ceiling infrastructure. And again, that really helps out the benefit to the full network and everybody who's in it. Now, where are we today? Align is currently running a large fleet of FPGAs in Canton, Ohio. We have a data center there. We have a 200 gigabyte pipe. And we have a lot of chips that are sitting on the shelf ready to be deployed. So we can build out different types of compute pipelines for different use cases. And so we are actively looking and building different types of compute that based on what we see out there. So yeah, it's, I wanted to talk to you guys to open myself up to communicate as you're building out your different compute use cases on the front end or wherever, however you're building it out. You should talk to us because we should work together. If there's big opportunity there, you can use our infrastructure to start to build out your compute pipelines. So feel free to reach out to me. You can always get in touch with me at my email or on my Filecoin Slack. Info's right there. So yeah, I'd love to talk and open it up to any questions.
Thank you, Svetly. Super helpful. And I just want to kind of launch one question with you there. If someone wants to engage with Aligned, is there any typical timeline process in terms of, let's say we identify some compute that could benefit from custom hardware? If you could maybe give us a sense of what the ballparks would look like. How do we do a proof of concept? How does that eventually get into larger rollout? Any sort of timelines around that would be super interesting.
Yeah, I mean, we can build out a proof of concept fairly quickly. The only thing is, as you know, we're all resource constraint is a big challenge for startups. And so right now we have specific focuses, and if it's a big opportunity, we would love to hear about it and work with you. Now, the timeline, it could be weeks to, we could actually spin up something in a week or two to something that takes a bit longer depending on the job. So I really can't say. It really depends on each individual job, but I encourage you to reach out to me with these use cases if you have something, so we can map out, what's the opportunity here and does it make sense to build something out for it.
Very good. And Zishan, feel free to jump in. It looks like you might have a question. Just go ahead and jump in whenever you're ready.
Yeah, just a quick question. I've done some FPGA work in the past. Do you guys allow any access for working with higher level languages on top of Verilog or VDHL, like HardCamel or something like Clash or Clasp or Haskell? Like, is there ways to kind of kind of operate more with the software and kind of libraries and stuff on top for programmers who want to operate workflows in your environment?
I mean, that would be a great question to ask my tech team. I think we could open up an API, right? So it doesn't matter what language you have on your end. We can always have an API to talk to our system, if that's what you mean. Or are you talking about like actually integrating your software deeper within our hardware?
Okay, cool. Thank you.
All right.
All right. Well,
this is super helpful, Svetly. One of the other things that I see coming along the path a lot is you mentioned ZK algorithm, zero knowledge proof, and zero knowledge proving. That area holds a lot of promise for folks to fix a lot of issues around private data sets, machine learning. People talk about using ZK for distributed learning and things like that. So I'm really glad to hear what you guys are working on in that space, because anything we can do to overcome these hardware limitations and bring more of these use cases to market, I think just helps all of us in the decentralized compute space. So thank you.
Absolutely. And, just to add, we really do have a big focus on the ZK proof side. So if you do have ZK proof use cases that you want to bring to us, we would love to talk more about those. Yeah, just let's keep the communication going, and let's see how this all evolves.
Very good. All right. Thank you so much. Cool. Well, we can, I think, hand it over, unless anybody has questions, to our next guest, Alexander Borzunov from Petals.ml. If you can hear us, Alexander.
Yeah, sure. Hi, everyone. Thanks, Wes, for inviting me to give the talk today. So let me share the slides. Do you see them?
Yes, looks good.
Yes.
Yeah, great. So, okay, let me start. So my name is Alex, and today I'll present you our new system called Petals. This is basically a decentralized platform for running large language models. I mean, the same size of GPT-3 maybe. And by the way, like if you have any questions during my talk, you can just like drop them in the chat, and like I'll try to answer them either now or after the talk. So okay, let's begin. So just to give you a quick background, I think most of you have already tried large language models, maybe as GPT-3 or like ChatGPT or another like chatbots and so on. But just like to give you a brief background, like the main feature of large language models is that they can solve many language processing tasks, not only like chat with other people for entertainment, but solve many practical language processing tasks out of the box or with really minimal fine-tuning. So like as an example, here on the left picture, we have like, so imagine, I don't know, maybe someone creates a chatbot that accepts some order for delivering food. And I don't know, a few years ago, you would need some NLP engineer to parse this sentence in English in human language for you into some like JSON format that you can later process in your like database in your delivery system. But now you can actually give like a few examples. Here it's enough to give just one example of what you want to do with the input text, basically to convert it into this kind of JSON, and you get you make the model to convert any later text for you. So you provide one example of response and it does it later automatically. And often you don't even need one example. You can just describe the task and it understands what it should do and just generates, for example, code, a line of code, or maybe like a longer text or code. And importantly, the language models can be used not only for generated texts, but you can use their internal representations. So you can basically cut off this head that chooses the next character and use these representations for basically many other things, such as maybe building a recommendation system, classification, and so on. So basically very useful for anything related to natural language processing and code processing. And as probably many of you know, modern LLMs are really huge and they keep growing. Like many of these few shot and zero shot properties arise at 100 billion plus parameters. So GPT-3 is 175 billion parameters and they keep growing. So like there are now like models close with 2 trillion parameters and so on. And of course, like at first, all these models were just proprietary. So companies like OpenAI, maybe DeepMind had them, but there was no much access to them from like people not working in these companies. Maybe we had like some APIs, limited APIs, or we could try some limited features, but we didn't have full access for research, for like implementing different stuff, different methods with these models. Like I think last year the situation has changed because multiple large models were released, most notably Bloom by the Big Science Initiative and Meta AI by Meta or ex-Facebook, and several other models. But turns out it doesn't really change situation much because only a very little number of people were able to actually run these models. And this is because they're really huge. So basically, if the model is of size of GPT-3, so have something like 170 billion parameters, you need at least this number of gigabytes of GPU memory to run the model efficiently. And this is even if you use like some very smart compression techniques. So if you just store each parameter as a floating point number, you will get like twice as that, or maybe 4 times as that. So anyway, even with the state-of-the-art compression methods, you can only run it if you have like really lots of high-end hardware, such as maybe 3 A100 GPUs with lots of GPU memory, or maybe 8 of more consumer-grade GPUs, 3090. So it is actually, this hardware is very expensive to buy, quite expensive to rent, and it is still difficult for like independent researchers or maybe small labs, small companies, university labs to use all of this. So actually, let's take a look of what options did we have before Petals. Actually, okay, like you can download this model, assume that you have maybe only like one consumer grade GPU, or maybe one high-end GPU, but not like a GPU cluster. So one method you could use is you could like take one machine with a GPU, then like when you run the model, basically copy model blocks from your disk or RAM to the GPU on demand. But this way, it turns out to be like extremely slow, because to generate even one token, even one part of the word, you need to go through all 70 transformer blocks of these like large language models. So you basically load it part by part. And to generate even one word, you need to transfer like almost 200 gigabytes to the GPU memory. And you need to transfer it for each word. So this turns out to be very slow even if you just copy this from RAM. In this case, it consumes like something like 20 seconds per token. So definitely this is not close for anything you could use to like make some interactive inference, make chatbots for any like practical applications. That's not quick enough, unfortunately. And it gets even slower if you don't have 200 gigabytes of RAM and you only use offloading from SSD. Okay, and another obvious option is that you could, maybe you don't even have a GPU, but you could use some hosted APIs from OpenAI, maybe other companies, and they are very convenient, of course, but they may be expensive, unfortunately. And also, you cannot always use custom fine-tuning and generation methods needed for your specific task. And this is very important for machine learning because, as you know, this is a very hot topic and new methods arise like many times a week. And you often want to apply some late paper, but you don't have access to, for example, code behind Hugging Face API or OpenAI API to implement some new features. And there's no way to look under the hood that's relevant for researchers. You only get the output text, but you can't analyze what happens in the model under the hood. So that's where basically Petals comes in. We suggest a new option here, a new option for running large language models if you don't have a GPU cluster yourself. And this is basically by collaborating with others of the internet, as some of my colleagues say, in the style of maybe BitTorrent or some other decentralized projects. So the core idea is that you load a small part of the model, then team up with people serving the other parts to run inference or maybe adapt the model for your own tasks. And just to give some terms here, so we have some participants called servers that load the model blocks, for example, BloomZ or maybe any other large LM. They load them to their GPUs and they kind of set up a service for others so that they can do like forward and backward passes, basically computations through these blocks they have already loaded to their GPUs. And of course, we have some clients who perform like forward backward passes through the whole model by successfully sending requests to the servers. So basically, maybe we want to send requests to the servers holding the first third of the model, then to the servers holding the second third, and so on. And it may come actually as a surprise because I've already told you that like running model locally, if you don't have enough GPUs, is like very slow. And here we now not only like run something locally, but now we also communicate via the internet, and the internet is relatively slow network compared to some like local networks in high performance clusters. So you may wonder like why is it faster? Because like internet is faulty, it's possibly slow. So it came for me, it came as a surprise that this way actually generation is at least like 10 times faster than with offloading, than with this method I told you for running the model locally. And why is it faster? Turns out this is just because, okay, even if we use like the internet, a very slow and possibly faulty network, we do not send much data this way. And this is because in the offloading case, we needed to like constantly send huge model blocks. But in our approach, every peer can just load a certain part of the model like to their GPUs, and then just like accept small requests with small internal representations of the model to like do their part of the job. So basically, to sum up, we use a slow network, but we send thousands times less data. So this actually works faster, even though some peers may leave, or even though there can be faults related to the unstable internet, for example. And also an important feature is that you can actually have lots of control over the model that you didn't have like in the hosted API case, because you call part of the model like yourself from your client that runs locally on your PC. And you can, for example, if you want to take a look what state the model had after a certain block, or maybe insert some new features, insert adapters, maybe change the order of layers somehow. You can do this with the as you do this like in the usual machine learning frameworks, and this is something that is not possible usually in the APIs. Okay. Let me take a look at the question. Is a history available for transformation models throughout its life cycle? Not sure I understand the question correctly. History is not stored by, almost all history is not stored by default, but to generate longer sequences, you need to store some of the latest hidden states to be able, so that the transformer is able to take a look at them. For example, if it needs to like generate newer texts that corresponds to the previous texts, and these one are stored while the inference session, while the generation session is open. So yeah, let me go further, and feel free to ask more questions, like if I didn't respond very clearly. So, okay, so the generation is fast, but here's another problem. Actually, it's not clear. So basically, all the peers have a common shared model. And what if they want to adapt the model for their own tasks? So maybe teach a new language for the model, or maybe teach a new task. So basically do anything that implies changing the weights of the model. Like, is it possible? And it turns out that yes. Basically, even if we assume that all these shared blocks hosted in servers are constant, modern NLP suggests that you can use some parameter efficient adapters or trainable prompts, basically a very small additions to the model compared to the this size of the pre-trained model, to adapt the model for like most real world tasks. So basically the pre-trained model, it kind of stores all the knowledge about the world it has learned from the internet and code and so on. And you can add just a very small adapter to adapt it to the task you need. And this adapter, it doesn't need much memory or compute, so it can be even stored locally, even on CPU at some cases when your client doesn't have a GPUs. Clients can store adapters in prompt locally and just train them as usual neural network using usual frameworks like PyTorch you're used to and so on. So this allows to clients to adapt the model for their own tasks, then use the common infrastructure, the common petal swarm to be able to run their version of the model, their adapted version of the model. And moreover, clients can share the trained adapters among each other, maybe publish on Hugging Face Hub or GitHub the weights, the small additions they have trained, and import them from each other. And of course, inspect some intermediate states for research, which is important for ML scientists. Okay, and yeah, before I show you some examples, some technical stuff. So the crucial thing is that we use libp2p for all the networking. So this allows us to have protocol agnostic networking code. So maybe it's some peers want to communicate over TCP, maybe the others want to communicate over over UDP, because this is more convenient for UDP hole punching. Basically, the only way we can communicate with UDP hole punching is to use QUIC, not TCP. And we can actually, this allows us, so if someone, for example, some user decides to join Petals, basically provide the computing power of their GPU, maybe their GPU at home or at their company. Usually they have NAT or a firewall, and libp2p allows us to use lots of NAT traversal techniques, including and also importantly circuit relays, to traverse that if a user didn't manage to set up the port forwarding correctly. And just like a small technical detail that may be interesting to people from protocol labs, that actually like Petals is written in Python, but we still use like the Go client for libp2p, and for this we kind of revived Go libp2p daemon that was unmaintained for a few months or maybe even years. So this allows us to use all these features. Yeah, and importantly, the whole system is decentralized. So like we don't have any like critical point of failure. You can even like a couple of services I'll show you later, you can just clone the repository and set up a replica of them yourself. And like there is no nothing in the system that cannot be replicated by other people, except maybe the bootstrap peers that we like, these bootstrap addresses that we have like in IPFS. So yeah, and importantly, all steps are fault tolerant. So of course, like people may leave at any time. Maybe they want to use their GPU for something else. And the clients will always be able to find another server holding the same blocks. And a couple of words of how to make this efficient. Basically, we need to compress anything so that like we can use as few servers as possible, as few communication as possible. So we compress model weights with different latest techniques. Don't actually store them in floating point numbers, but rather in some quantized state that involves like just an index in the like some bin where the weights falls. Also the same for communication and so on. Well, okay, and of course there is some like load balancing. So basically, first of all, if some servers leave, like imagine in this picture, like turns out like all these servers leave and we have a gap in the network. The other servers are able to change the blocks they hold to close this gap or maybe a bottleneck. And the same for clients. So clients may choose servers to optimize latency for generation, to optimize throughput for training with larger batches, because throughput is much more important than latency in this case. And of course, like there is some randomization so that we don't always fall into the same pass, and we're kind of trying to distribute the load over the network. And now I'll just show you a couple of examples. So right now, our public swarm hosts two models. So these are Bloom and BloomZ. These are basically kind of publicly released models that are similar to GPT-3 maybe. They are of the same size as GPT-3. And Bloom is a regular language model, and BloomZ is its version fine-tuned to follow human instructions. So basically that's maybe something closer to ChatGPT, because the standard language model may refuse to follow your instruction, but this does its best. So yeah, we have two of such models, many servers contributed by different users and organizations of different capacity that allows us to like form the full chain. So basically both of these models have 70 blocks, and the client, when it wants to generate something or train an adaptation of the model, they choose a chain through all these, through all the available servers, given the conditions they want to optimize, and then run the model with maybe like a decent speed. So our speed is something like 1 token per second. This is not blazing fast, but this allows you to have some interactive applications like chatbots, or maybe like show a beautiful progress bar to a user that like spins for 5 seconds and then they have like their response and so on. And as an example, we have like this chat. It is of course not as strong as ChatGPT, because we didn't spend that much time on the modeling side, but still it runs to run this BloomZ model, the model fine-tuned to follow the human instructions and see its outputs in real time as soon as it is generated by the swarm. So it should work with 1 or 2 seconds per token. Sometimes it's slower because sometimes we have lots of clients, and of course we need more servers joining to handle increased loads properly. But anyway, this works, and without Petals, like you couldn't actually try BloomZ because it's not available yet in most inference APIs. So and like inference with offloading is like 20 seconds per token. So this allows many people to try this model now. And if you are an ML engineer, a machine learning engineer, it is important that we made Petals interfaces look so that we made Petals interfaces so that Petals is no more difficult to use than running on a small model on your PC. So basically all these interfaces are very similar to a popular Hugging Face transformers library, and you kind of just create another models. And if you're just an ML engineer, you don't need to know that like under the hood, there are like huge amount of algorithms, all the libp2p stack and so on, like lots of going on. For you, it's just like the usual model you run. So basically that's mostly it. Some points about the future work we may do. So we consider introducing rewards for hosting servers because of course there may be some imbalance. For example, if it turns out that many people made some client applications for Petals, but not many people decide to like join as servers. So yeah, we wanted to introduce some rewards that will serve people hosting servers will then be able to use them on high priority inference, and maybe some extra features like increased text lengths. We do not consider like any crypto at the moment. It will be just like a simple reward system because like our system Petals is ML focused. But anyway, I hope this will motivate some people to contribute. Also, we wanted to make like a leaderboard of who contributed the most, so people can kind of advertise their companies. Maybe, for example, you own a GPU hosting and you can like provide a couple of GPU and advertise its name in our leaderboard. Another important point is like security. So basically we want to solve it by validators pretending to be clients and periodically checking if servers return correct results. And of course, if they kind of cheat, if, for example, they may want to cheat to earn points without actually contributing compute. If they cheat, we can like ban them and maybe make some subtract some amount of their points and so on. And I would say that the most important downside of our system compared to other approaches is privacy, because peers in the public swarm may recover parts of your data. That's unfortunately how it works right now. Of course, there are like a lot of stuff about like some multi-party computations, like maybe ZK proofing, but that's more for security and so on. But unfortunately, this does not work for machine learning, for large-scale machine learning well yet, because it usually involves like 10x or 100x slowdown due to the fact that these methods usually work with some like, integer discrete maths, and like machine learning is a completely different field. You calculate everything in floating point numbers, and like these algorithms, these MPC algorithms, they're not translated well to these floating point numbers. So you have lots of conversions. So anyway, like we think that unfortunately it's not practical to apply any known MPC methods here yet, but maybe some methods will appear in the future. And for now, we suggest just set up, if you still want to use Petals, for example, you are in some university lab that wants to process some private data, you can set up a private swarm between organizations you trust. Maybe, I don't know, join with another small company, another university lab, and you can easily set up a private swarm, basically a private libp2p network where all the data will be processed among the peers you trust. So it won't be, and security and privacy won't be issues for you. So basically that's it. You can check out our website. We have like GitHub, docs, tutorials, everything there. Also a paper if you want to dig into technical details. And feel free to ask any questions now.
Alexander, this is amazing. Huge fan of the work that you guys have built. I mean, in so many ways. I'll start with one question, and I have a lot more, but I'll give some other folks an opportunity to weigh in. Could you share a little bit about when you were starting the network of compute providers available in your network, people that are actually running the Petals software? Could you talk a little bit about how you grew that network? Was it simple word of mouth, or did you have any more sort of intentional way of growing that? And maybe what you would like for it to become in the future?
Yeah, sure. So basically it grows at some rate for now. So basically we got some initial visibility because like Bloom is a very popular model, and like indeed many people, like indeed running such large models were an issue for many people. So we got some visibility on the like ML subreddits, maybe ML Twitter, Hacker News. So like some people just came to try it out. It's not difficult for some people like to host a couple of servers because they may have like a couple of spare GPUs. But of course, like we do not grow with a very quick rate yet. And that's why we want to work on like introducing incentives as fast as possible so that like people are more motivated to do that. However, like I think still now the growth rate is not zero. I suppose it's like something similar to BitTorrent, maybe, that does not provide any explicit incentives, but the people are still like sharing files because kind of, I don't know, maybe they want to give back to the community or something. Yeah, did I answer your question?
That's perfect. Thank you.
Yeah, great.
Yeah, it's a testament to the interest right now in the language models that you guys are serving.
Yeah, if you have any spare GPUs, you can also connect.
What is the kind of like, what's the current traction that you're seeing? And when you look at it, I don't know, you're 2 years out, like what's the opportunity? How do you quantify it for a team that's looking to do something that's more commercial, more scaled, and like less on the science fair project side?
Yeah, so we're actually a research team. So like Petals is not a startup. We're just like researchers at a lab, and so we decided to make this project with like other researchers from the Big Science collaboration, basically a collaboration that unites all the researchers from lots of different universities and companies. And so we actually don't want to monetize it, don't plan to monetize it to get any profit ourselves for now. So I think our primary focus for now is to just make some kind of self-sustainable system, like maybe BitTorrent or Bitcoin. So maybe you will move on to any other project or company, but the system will live. Maybe someone else will be able to like contribute and so on. So yeah, we don't have like explicit plans for monetization, and only want to add incentives so that like to balance the demand for the servers and supply. But these incentives, they are not like planned, like, you know, they won't be designed explicitly as money like crypto tokens. So this is like something you can get, something you can spend for useful features, but not really any kind of a token or something.
Makes sense. I guess what I'm trying to get to is like, what's that thing that would cause an inflection point, and what could it turn into? So with my team as well, we're not looking to mine crypto tokens. It's offering compute as a service, but you know, like how do you get a team like our team to develop a pipeline for this, to offer, you know, for the reward? Like, can you define like, okay, in a year or 2 years, we think it could be this big because of this inflection point? And I think someone's asking like, what universities are you working with? Maybe that's kind of the path. Is there a partnership or something that you need that would cause that growth?
Yeah. So right now, yeah, we're thinking about different like ways, to spend to award points. So yeah, thanks for the suggestion. So yeah, I guess we need to like take a look at different approaches, because there are like lots of similar networks awarding someone for computations out there. So yeah. But for now, I can't like say any specific plans.
It's very cool. Thank you.
Yeah. So a question from Irina. Yeah. So yeah, where I'm based, I'm currently in Armenia. So yeah, my university. So yeah, we are actually like a research lab in Yandex, in the Yandex company, and but we're kind of very independent, because we don't do anything for business. We're mostly focused on like science thing and contributing papers. And we did this project with people from many other companies, like on the first slide, like people from also Hugging Face, that's a well-known company in NLP field, also from people from University of Washington and so on. Yeah. Thanks for the link. Yeah, with people from big science, basically. Yeah.
And the last question: what's your top priorities in the roadmap? Your road?
Yeah, sure.
Mhm.
Yeah. So basically, I think our top priorities now is to. So first of all, we want to finish this incentive system, because it is important to like match the demand to handle the growth more naturally. Also, we wanted to do like some technical optimizations. I'll move to this slide. So basically, there are a huge room on in improvement the routing algorithms. So basically, choosing the path among servers so that works as fast as possible. And also we can consider like implementing some stuff like tensor parallelism. So basically, if you have one machine with a few GPUs, right now you need to like run n Petal servers, but you will be able to run one tensor Petal server that will be like n times faster. So basically, this also will decrease the inference time. So yeah, I think that's basically it. So incentives and some work on making the network more fast and more stable.
Thank you.
Are there is there any understanding of like asymptotic limits of how well this could perform relative to like models being run all in one location?
Yeah, so there is something you cannot surpass, is that like basically you can optimize the computations that are done like inside one server, but you cannot optimize much the latency between servers. So basically, for example, right now for BloomZ, you will need 3 hops at best. So basically, if you choose the long server from like 0 to 16, then this server and this server. And you can optimize something that happens inside a server, but the latency between them stays. And I think this can also be optimized to some point, for example, by choosing servers geographically closest to you. So, for example, I imagine that if the network grows, we'll have servers in America, in Europe, maybe in other continents as well. And the clients will be able to choose closest servers to like minimize all this latency. But still, there is some, I think there is some lower bound that we won't able to surpass. And of course, this will never be as fast as inference on like a GPU cluster, but we can become close to it, more and more close.
Also, are there like, what are the main differences between training and inference in these models? And also you did go over training somewhat, but it was also those models weren't being trained from scratch. So is it also, so what's the story with training models from scratch?
Yeah, so actually, like our research group started from like approaching how to train very large models from scratch, because I think they started in like 2020, and I joined soon as well. And at that point, there was like GPT-3, but there were no publicly released models of this size. So we thought that maybe we need to make a system for training them from scratch to get them. But actually, like, turned out that this system, like we made a library for this. It's called HiveMind, and actually Petals uses it a lot under the hood. So like we built on our previous work, but HiveMind, in my opinion, it turned out not as popular because to train large models from scratch, you need like lots of ML expertise, like much more than like you need to just like fine tune it for something or run a chart and so on. And turns out there is not too many people out there who don't work for a certain company yet and who want to like create these large models. And it was much easier for them to find some funding, find some like donations, basically, than to set up this complicated distributed training system that like uses Sleep P2P and many other things. So basically, yeah, HiveMind turned out to be much more complicated, though you can still use it to train like models from scratch. Maybe not 100 billion plus, but I think like 5 or 10 billion definitely works. Yeah, and so yeah, a lot harder for open source, as Alexandra writes in the chat. And yeah, and as for the difference from between training and between inference and fine tuning, so like right now, basically, an important difference is that you usually do inference like for one sequence or for a few sequences in parallel, and you usually do training for very large batches of examples. So you need different routing algorithms on client to perform them efficiently. So like inference should optimize latency, and in turn, latency is not important for training because throughput is much more important, because like you transfer lots of data, then process a huge batch, then transfer them, and so on. And yeah, and for inference, another important consideration is that it consumes memory, because like people, for example, if you're talking to like our chatbot, you need like while you're talking, all the servers in your inference chain should store all the previous like states for the previous tokens, so that the transformer can attend to it, so it can look back and understand what you were talking about, and so on. So inference consumes some memory. That's what called cache in this table. So basically, it consumes some memory, and you need to allocate some memory like for a long periods of time to like allow to do inference.
Got it. Thank you.
Mm-hmm.
Alexander, one last question here. I know we're getting a little close to the end of time, but I'm super interested the checking, the validation that your team is doing for potential cheaters in the system. Could you just give a high-level perspective when you're thinking about designs for looking for malicious behavior or cheating behavior? Do you try to approach it in a programmatic way, or is it somehow more of a manual task? That'd be very helpful, because a lot of other projects are concerned with similar problems.
Yeah, sure. So our security system that we want to start with, this is definitely not like a silver bullet. It won't be perfect, but I think it will be able to like catch like some, maybe at least hardware failures, or people who didn't spend like multiple weeks to dig in all our stack and so on. And what we want to do is basically to just make these validators who pretend to be clients and send different kinds of requests to the servers, and then they like know the correct answer in advance, because like we may pre-calculate it, or maybe we can calculate it using like a subset of trusted servers, because like there are a couple servers hosted by us in this like scheme. And yeah, we can compare that. And for example, if you assume that there is present some malicious server that maybe not all the time, but with a certain probability responds with incorrect data, it will be catched sooner or later. Like, of course, it will be able to harm to a couple of people, but it will be caught sooner or later. So that's, I think, good enough to start. And like for increased security guarantees, the clients will be able. So one thing you can do is just to run, for example, inference through multiple chains, through like 2 disjoint sets of servers, so that you can like double check your result. And also, of course, like for 100% guarantees, you need to use a private swarm in this scheme, unfortunately. Yeah, unfortunately, there is no like good proof of work for neural networks at the moment. So
Super helpful. All right, I'll give just another second in case anybody else has one last question. And if not, we will thank you so much for joining, both you and Svetly. This was tremendous content. Much appreciated. I'm going to post this recording to the Slack channel soon under the Computer Over Data Working Group. If everyone goes to cod.cloud, they can get a link to the Slack channel there. And obviously, Svetly, Alexander, we'd love to have you guys join us there for any future conversations. But just to wrap up, thank you so much for taking time. Love what you guys are building, and we appreciate you for joining.
yeah, thank you for inviting me. Like Protocol Labs, we use a lot of your stuff, and I think like we're very happy that you invited us.
Yeah, thanks everyone for your time. Really appreciate it.
This
Thank
was
you both.
awesome.
Awesome presentation.
Thank you.
Thanks everyone.